Hello and welcome to another Func Prog Sweden. My name is Magnus and I'm the host and organizer of Func Prog Sweden. Func Prog Sweden is the meetup where we explore functional programming languages and functional programming concepts. And to further spread functional programming, as we announced at the last meetup, we've started a podcast also called Func Prog Podcast. Christopher Ekeroth is the host, and if you want to find out or listen to more content between our meetups, you're welcome to join in and listen to the podcast. You can find the podcast on the YouTube channel, of course, where all the other presentations are, as always, available, or on Spotify and Apple Podcast and whatnot. With that, let's head over to today's agenda. First, as always, a short intro by me, Magnus, and then we head over to an Algebra of Thoughts, when Kio Effects meets LLMs by Flavio Brasil. Then we'll do a post-show chat. As you can see, we've updated the agenda a bit. Unfortunately, Patrick couldn't join us because of personal reasons. We hope we can bring Patrick on and his presentation on either on the next meetup or on the coming meetup in August and onwards. As always, we would like to thank Beat, our video sponsor, that's been with us for all the time here at Func Prog Sweden. Thank you very much, Beat. And if you want to know more about Beat and what they're doing, head over to their webpage, adabeat.com, or check them out on social media. And also, we want to push a bit. We're going to run something called the Func Prog Conf 15th of October 2025 in Stockholm. It's going to be an in-person half-day event with 3 presentations, one in Scala, one on Gleam, and one on Haskell, and then in the end we'll do a panel. So if you're in Stockholm, head over to Func Prog Conf. You can find them on Google. If you Google it, buy your ticket. It's going to be a half-day conference, and it's going to be great. Then, coming schedule, 10th of June, we'll run the next meetup. Then we haven't set the date yet for August and not for September, but we'll for sure come back with dates. And then, as I already mentioned, 15th of October, we'll run the Func Prog Conf. Welcome to join. If you want to support the meetup, head over and join the meetup group. Make sure to subscribe on YouTube. And if you want to ask more questions, interact with other members of the community, head over to the Discord server. You can find the invite either below here or on YouTube or on the Meetup group also. And if you have any questions during the presentation, please shoot them in the chat or in the Discord server, and I will convey it to the presenter. With that, let's get started. Welcome to Func Prog Sweden, Flavio Brasil. Warm welcome.
Hi, thank you, Magnus. Thank you for the invite.
Yeah, you're warm welcome to Func Prog Sweden. We are so looking forward to your presentation, an Algebra of Thoughts, when Kio meets LLMs.
Great, cool. So, hi everyone. My name is Flavio Brasil, and I'm going to be presenting about a project I've been working on for the past couple of years that is called Kyo. And it's a library in Scala that is a new effect system with some innovations, algebraic effects, and etc. that is quite interesting. But today the focus is going to be a new set of modules, a new repository with the implementations for interacting with large language models, leveraging the features in Kyo for a better experience developing solutions with AI. So just a bit of me. Oh, I'm also going to mention the illustrations is by James Audubon from The Birds of America. I really love this book. So I used for the slides. So just a bit of me, who I am. Today I'm actually with my open source hat. So this is not about my day job. This is really a passion project. So something that I work in my free time. And it's really, I've been doing that for years. That is using open source as a way of finding ways to innovate and build different solutions. And that's like part of the work in Kyo that I'm going to be presenting today. And I'm also, my day job is as a principal engineer at Nubank. A lot of my career is focused on performance engineering, but more recently I decided to go more on the product side. So I'm working on the core banking systems at Nubank now. And Nubank is a large fintech in Brazil. Just the outline of the talk is three main topics. I actually have a lot to cover, and it's going to be a lot of code. So if you have any questions later, I'm going to be sharing the slides and etc. So feel free to reach out. So the sections are basically introduction to Q, that is just a brief introduction of the library itself, so you can understand the primitives with the LLMs, and then the presentation of the primitives for LLMs, and some idea of what's next for us in terms of planning in the project. So let's start with the introduction to Q. So Q is a new functional programming library in Scala, so it's an effect system, but we are planning the project as a like a framework, right? So for example, if you have a Spring where you have common sets of modules where you can do like everything that you need to do in software engineering with like different integrations, different solutions, but within the same patterns, the same ecosystem to provide a good experience to the user, right? So that's one of the main goals in Q. We have a lot of focus on modularity. So if you see the implementations are very modular, like everything is well isolated. So to have like a good set of APIs to the user, right? So if you are using Kio's effects, you can see that they are like handling a single concern and they have like canonical APIs. So you can reduce the API surface and provide better usability that way. And we also have this focus on performance because of my background and the other main engineer in the project, Adam Hearn. He also really likes working with performance, so it's a major focus of the project. Another thing that we decided to do in Kyo, even though it's based on functional programming and more advanced topics in functional programming, we don't expose any of that to the users, right? So you won't see like math concepts in the APIs or in the solutions. We also don't use symbolic operators in the project as well to make it it's possible for newcomers to onboard in functional programming in an easier way, right? The library is also based on algebraic effects, so it simplifies functional programming because it takes away that issue of having multiple monads and then monads nesting and monads composing them. It can be really complicated, especially for people that are adopting. And simply algebraic effects basically allow you to mix all the effects into the same computation without all these complications that you have from different monads. We also have direct syntax support that is essentially like async await, but generalized to all effects, so algebraic effects in general. And another focus of the library is providing good type inference. So the library is designed so you can write codes without declaring types or declaring in very few places, right? So that's something if you are like coming from Python, these types or etc. Like Scala 3 can be already better in terms of syntax being closer to Python, and Kyo providing this experience with better inference also can be something good for someone that's coming from an untyped language. And we are close to the 1.0. We've been working on the project, I think, almost 3 years now, and we are close to releasing the first release candidates for 1.0, and we are going to do a few releases, but the goal is to have the 1.0 release in the next few months, basically. So just an example of how Kyo computation looks like. This is when we are reading, performing side effects, for example, interacting with the file system, disks, and basically doing anything that's not only a pure computation. In functional programming, we have to suspend those effects, right? Suspend those side effects. So we can, that way, compose multiple effects together in a way that's safe and it works well. And in this case here, we are suspending a side effecting operation that is reading a file. And the way that we are suspending is using the IO effects.apply method. And that's going to be creating a computation that's a description that what needs to happen. But it's not going to be executing not anything at that point. And that produces what we call a computation that is a Q computation is the pending type. So in this case here, let's say that reading the file produces a string. And then we have this lesser than sign. It's actually a type, right? So the way that we are using it is an infix notation for types in Scala. So it looks different, but it's actually just a regular type. And the first type parameter is the result of the computation. So in this example, the computation is going to be producing a string, right? But the computation also suspends with the I/O effect. And because of that, we have then the I/O effects pending in the second type parameter. So essentially, this means it produces a string and may perform 0 or any number of I/O suspensions during the execution. And the way that we read it, because we call the lesser sign as the pending type, so we read it like string pending IO, right? So what is the result of the computation, and it's pending this effect IO. And it's not executing because this effect is pending, right? And then another example here is we also have this memo effect, so this for memoization. It's something that's useful when you are initializing services because you don't want to initialize a service multiple times because then you have multiple clients and you end up like resource waste that way. And the memo type effects can be used, for example, in an initialized service to ensure it's initialized only once. And then here it's a service pending the memo effect. The second example is calling a method from the service, and I'm assuming here that it's like a network service, so it's going to be asynchronous. Because of that, we have a response pending the async effects. That is basically indicating that the computation has points where it's going to be parking because of an asynchronous boundary, like calling a service or waiting for some asynchronous operation. And the last one is a bit more involved. If you see the implementation, I'm calling env.use, and env is another effect that is the environment effect. So basically, you can summon out of thin air an object. So here I'm asking, I'm going to use the service from the environment, and then I'm going to call the method of that service. And as we have the two effects from A and B, and we are sorry, from the environments and the call, we have the environments pending because it means the computation is waiting for a service to be provided. So at another place of the computation, you have to provide and handle that effects. And then there's the async call because the service might be performing asynchronous computations there. And the way that we represent multiple pending effects is through a type union. And once you have more than one item, you have to add the parentheses because of Scala syntax. But here we are pending, so we are response pending the async effect and an environment of a service. And we have multiple effects, so I'm not going to go over the details, but bars with precise handling, that is something that other effect systems don't have. Like you are able to handle one specific failure out of a set of possible failures. There's the environment effect that we just saw with dependency injection. We have aspects that are it's very interesting because it's a very small implementation, but it has the same properties as, for example, aspects in Spring that has a lot of code to work, right? So it shows like how powerful algebraic effects can be as well. We have parsing as well, the same thing of like no symbolic operators to make it easier for people to adopt. We have like string, batching of remote calls to services, channel, clock, signal, latch, meter. It's basically mutexes and semaphores, software transaction memory, and there's a lot more. So we've been growing the library very quickly the past couple of years. So it has a quite comprehensive set of primitives for building asynchronous, especially backend systems in high performance environments. And if you notice the way that code is structured, we have this focus on providing to the user concrete primitives. So if you see something in code, it's actually something useful that you know that's going to be doing something useful to you. So it's not like an abstract functional programming concepts or something like that. It's really just algebraic effects, and each effect is something that is useful, something that you can use, and it's concrete. And you won't see, as I said, like any functional programming concepts leaking to the user. So no monoids, no Kleisli, no Koyunida, like none of these abstractions leaking to the user. And it's possible to do functional programming, principal functional programming that way. It's not necessary to actually expose the users to those concepts. So that's like just an overview of the effects, and we have like a collection of effects, and the computation, the pending type declares effects that are pending. But then we need to compose those effects, right? So how can we take a computation and plug into the other and etc. So I have another example here that is, the first one is just like suspending the creation of a list as an example. So it's going to be a list of integers pending IO, right? And the second one is just a method plus one takes a list and it's calling async.forEach. And this method is actually running in parallel. So it's going to process the list, call the function, and return another list with the results of that processing. And that's going to be in parallel, and it also has protections against like too high concurrency. So there's like something that's like really mindful of the performance of especially backend systems. And then the way that we can compose computation, so if we want to pass the list from my list to the plus one methods, how can we do that, right? So here I'm using the map methods. And I think maybe people are going to find that strange, right? Because if my list is a computation and then plus one is another computation, shouldn't that be a bind or flat map? And yes, it should be, but it is. So it means in Kyo, actually, map and flat map are the same signature. So they are both the same signature, the same implementation. They are just aliases to the same operation that is the monadic binds. And why that is possible is because when you have, for example, a value of type integer and you want to refer to it as a Kyo computation, like a integer pending IO, there is a mechanism in the library that's going to do this lifting out of a computation to the from pure values, pure plain values to computations automatically. So when you are mapping, the plus one returns a computation or returns an actual value, it's going to adapt automatically for you in the type system. It's not something at runtime, it's like guaranteed at compile time. And basically, both are going to have the same behavior, map and flat map. And that's something that helps a lot, especially for newcomers, right? So you normally have this issue of you have the map call, and then you have flat map calls, and then you have to lift values. And some people have trouble to get to that level of abstraction, especially at the beginning. Eventually, people can understand, but it's something that can be a blocker for the beginning in adoption of FP. And basically, merging the two is a way of improving usability because the mental model is very simple. Just take the computation, apply map, and any transformation that you want to make there without worrying about lifting or map or flat map. And here I just wanted to do an exercise because I think understanding how the painting type works and how the tracking of effects work is something that is more of a blocker for people to understand the library. So I'm gonna give like 2 seconds for you to think, what should be the type of my list in the first example here? So it should be a list of integer pending IO, right? So it's producing a list of integer and it's performing an IO suspension, right? The second one is using async.forEach. And as I said, for each returns another list with the processed elements. So in this case, it's going to be a list of integer pending async, right? And the last one, we have two effects being mixed there. So we have my list with IO and we have plus one with async. So what happens is it accumulates. As you are using the final computations, they are going to be using effects, and those effects get added to the pending set. And you don't need to keep typing it. You can use the autocompletion from the IDE, or you can even not declare the types in many cases. So you can have like a more fluent usage that way. And as I mentioned, the flat map is the same. So it returns the same type as well. There's a detail that I didn't put here, but basically IO and async, the async effect includes the IO effect. So we could have just async here, but I wanted to put both to show this property of the effects composing together. And then the last part of using Kyo is how do you handle those effects, right? So they are pending there, like what do we do with them? So the first one has the IO pending, the second one has that async pending. So the first one, I'm going to handle the IO effects, but it's something you shouldn't do. It should be in Kyo app, that is like the entry points of the application, because if you evaluate side effects eagerly, you break properties that allow the mixing of effects to be sound, right? So basically, you can't really guarantee that the effects are going to execute properly. So suspension of side effects is really important. So IO unsafe.run is something that you shouldn't do, but just as an example, in this case, if you notice, we had only I/O pending initially, and we don't have any other effects pending anymore. So that means that the pending set is empty, and we represent that through the Scala type system as an any type. So if you see an any in the pending type as the pending set of effects, it's basically an empty set. And you can actually call eval on that to get the final value, for example. And the last example there is handling the async effects. And I want to put these two because it shows the difference between I/O and async, right? So I/O is something that's synchronous, so it's not going to park, it's not going to have any asynchronous operations. That is different from other effect systems where I/O includes async, right? So in Q, they are separate. And then I'm handling I/O here, and I'm getting a fiber back, right? So and fibers have tracking of failure, so the nothing there means that the fiber doesn't have a type failure, no expected failures essentially. And then it produces an integer. And I actually forgot to put the pending IO there, but it would be pending IO. So the slide is incorrect at this point. So essentially, that's all you need to know to use Q, right? So there's lots of interesting things in the library, interesting concepts that come from functional programming. But if you want to learn and use Q, that's really truly the building blocks that you need to have and you need to understand. And if look at the library and the implementations as well, the effects are designed to have like a canonical, simple API. So it's an intentional process of simplification to get to those effects. And you can see that the code is also designed to be readable, right? So we have Scala docs, like documentation explaining the different mental model of how to use the effects, when to use one or another, and the characteristics of the effects. So I really recommend looking at the Scala docs to understand the library. Our README is it's not well maintained anymore, and I'm sorry, we are sorry for that, but we are going to be fixing that for the 1.0 release. I would say the source code of the library is the main documentation at the moment. So just to recap how to use Q, and all you need to learn to use Q is basically effects are these composable building blocks that you use in your computation. And as you use them, they are getting added to the pending sets of effects to be handled, right? So it's just accumulating there. Eventually, and then you can use map to do compose computations. You can also use for computations. There's also the direct syntax module in Q, where you can use like a single weight that is like in other languages, but generalized to algebraic effects in general. But basically like compose computations with map, there's like very simple API, even simpler than more traditional encodings of monads. And then you have to handle effects. So for example, calling some effects.run. So essentially the run methods are the methods that handle the effects. And each handler can have like different behaviors, different parameters, different results, depending on the behavior of the effect itself. And the thing that I wanted to highlight, you don't need to understand deep functional programming concepts. You don't need to worry about like understanding in depth like monads and algebraic effects and continuations. Really is just like this mental model of like using these building blocks throughout your computation, tracking them, and then handling those effects later when it's appropriate in your logic of the codes, right? So that's basically the introduction to Q. That's an overview. I hope it's a good way of understanding the library. And if you have any questions, feel free to reach out as well. And now I'm going to go to the main topic of the presentation, that is this new set of primitives I've been refining over time. And today I'm going to be, after the talk, I'm going to make the repository public, so you can go and check it out. But we are going to eventually maybe merge the new repository in the main repository, but for now it's going to be separate. The main goals of this new repository, this new work, is first and foremost accessible to newcomers. So have a way of structuring APIs and abstractions, for example, without having too many type parameters, or providing really good inference of the code as well. So providing a way of like newcomers to come and like learn functional programming, start adopting functional programming in a more gradual way, right? And in Q, we also have like a great way of adopting functional programming. So from a simple, more async awaits API, then to the monadic API, and then we have a more advanced module that is called combinators that is more similar to other functional programming libraries that are more advanced, right? And a lot of the work in this is removing accidental complexity. I don't know if how many people have experience working like with solutions with LLMs, but you have all these like little accidental complexities, like how can you define a tool? Or you have to define a JSON schema, and then you have to handle the request to that tool, and then you have to handle serialization depending on the library, right? And for example, you have to handle the context of the LLM, keep like a list of messages, and then adds when you get a new message. So there's like lots of things that are accidental complexity that it's not really about the generation itself, it's more about communication with the LLM. And a lot of the work in these new primitives is really to remove this kind of accidental complexity. Another focus is like composable building blocks, so following the same mindsets from the rest of the Q library. And in the end, after you look at the primitives, I think it's going to be easier to see that. But it's essentially instead of going, we are today in a paradigm where interacting with the LLM is basically this monolithic block of codes or block of prompts and etc. But I think we need to move to more like interaction with LLM, the request and response being like a programmable surface where you can mix things together. You can take some out, you can put another one, because then you can experiment with different things and different generations to see like the kind of behavior that the LLM can actually produce for our needs, right? So just an overview of these primitives. So the first one is the main one is the AI effect. And it provides structured inputs and outputs for LLMs. And it does automatic context handling. So you don't need to worry about keeping those messages. The library keeps for it the context. The prompts are dynamic, so you can actually fetch things from the database and like do service calls to form your prompts, and that composes well using Kyo's effects. So all designs around this composability of effects. And there's also a new mechanism of reminders for large contexts that I'm going to talk more later. Tool definition is just plain Scala. You just use like regular classes, regular Scala codes, no JSON, no like nothing low level. It's really high level. And there's thoughts. Thoughts is a new technique, I would say. So I've seen similar techniques, for example, in the instructor library in Python, but I haven't seen something more evolved like I'm going to present today. That is what I'm calling structured thinking, where you can both influence the LLM's behavior through structured generation, but also observe the LLM's behavior as well. So it's really good for business applications, for example. And then we have agent as well. So agents is just like a specialization of Q's actors. There is a Q actor module for LLMs. And then the last one is the modes. It is essentially like an interceptor. You can customize the behavior of the generation itself and even like generate multiple possible options. And then without having to change the actual codes, you just like wrap with the modes. And I'm going to show more, and you can change that behavior for all generations within a computation. So cool, I'm going to go through all these effects. I think it's going to be a lot of codes. I might go a bit fast. So please try to keep up with me. If you have trouble, feel free to ask questions as well. I'm available to clarify anything. So let's go to the AI effect. So if you ask me, how does an AI application look like in Q? That's it, one line of code. So when you are using the AI effect, the main method is the gen method. So it takes a type parameter that specifies what you want to generate, the LLM to generate. So for example, here I'm asking for the LLM to generate a string, then it's going to just reply, right? So my hello, for example. And that's going to be handling everything, like how the call happens, like everything is already set up and handled by the library. And that's going to be producing a kill computation as well. So it has the same properties, same characteristics as the other effects. So it's going to be string pending the AI effects that we just used. But then you might be thinking, oh, that's not really truly a full application in Q, right? So using AI. okay, this is a truly fully application using AI. So you just have like these entry points of the main of the JVM, but the implementation is really that. Like you can call AI gen and generate anything and even complex objects. And if you want to customize things, you can also, for example, say I want to use the configuration to use GPT-4o, and you can set the API keys here. You can also set, for example, rate limiting. That is a very important feature when you're developing with LLMs because of like token limits and request limits that's common to hit. And you can generate complex objects. So not only just strings. For example, here I'm just made like a made up example recipe, data structure, name, ingredients, and a list of steps. And I'm asking the LLM to generate a recipe. And I'm passing there a pastel. It is a Brazilian pastry, really great. So I decided to put it there. But essentially, the library is going to be handling generating the JSON schema for recipe, passing that to the LLM, and then the LLM is going to respond. The library is going to parse that, and eventually, if there are errors, there's like a handling of errors that does some repair for the LLM to work better as well. And then it ends up producing a recipe at the end. So you can just ask like for arbitrary data structures that way. Here's another example just showing that the AI effects and all these effects that I'm going to be showing, they play well with the regular queue effects. So for example, here I'm using async.forEach that's going to be executing, processing the list in parallel, so the two items in parallel, and generating the recipe for those two items in parallel. And that works like even like all the other effects, even more pure functional programming like var effects or batching as well, like it all plays well together. This is another example showing the automatic handling of context. So here I have the recipe, and then I created this other data structure that is recipe difficulty. That is just like an analysis of the AI of the ingredients that are hard to find and the steps that are time consuming, just like some elaboration of the LLM for that. And then I'm first calling the recipe generation, so generating the recipe object. And I'm using a for comprehension here, right? So in Scala, you can do, it's just syntax trigger for the map call, the flat map call. And then I'm going to generate these new objects, the recipe difficulty, right? So I'm just asking you for an arbitrary case class. How does it know which recipe we are talking about, right? So in the first call, I'm calling pastel, saying, okay, generates a pastel recipe. But the second one, I'm not passing anything. What's happening there? What's happening is the computation itself is the AI executing. It's a different way of thinking, but the computation maintains the context of the execution. So as you do generations, that's going to be accumulating in the AI context. So you don't need to manage that manually, right? So once you call the recipe difficulty generation happens, the context of the recipe for pastel is going to be in the same context for the LM to see. So it's going to be appending the messages there. And then you might be thinking, oh, we can't just like keep accumulating things, right? Because you have to isolate parts of the system, manage the context as well in certain situations. And there are combinators for that. So the main one is the forget method. So I'm passing here in the difficulty generation, I'm calling AI.forget and passing that computation. So what that means is that the computation within that scope of AI.forget is going to execute, and once it finishes, it's going to return the result, but the state of the context of the LLM is going to be reset. Right, so it's going to basically isolate the execution of the LLM at that point. And if you think of it, it's kind of like a transactional behavior, right? So if you have, for example, a workflow where you are performing multiple tasks in parallel, and then you're summarizing, getting information back, you can't really aggregate all the context of all execution. You have to keep summarizing and then forgetting things. So this process of like these combinators allow this kind of behavior. The next one is prompt. It's a bit different from other libraries because again, because of composability of effects, so being able to use effects with prompts. It has also this reminders mechanism. So here's an example of a definition of a prompt. Very simple. You can call prompt.init, and then you can pass the text that is the instructions to the LLM. That's going to become the system prompts at the beginning of the context. And then you call prompt.enable, and then you pass the computation that's going to be running with that prompt enabled. And as you can see, this pattern of composing things using scoping is really common. It's really throughout the library, and it helps a lot with composability. So, for example, if you had two generations here, both generations would be executing with that prompt, right? So, and you can even have nesting, like you can enable a prompt at a higher nesting, and then enable at a lower, like a nesting another place of the code, and that's going to be composing and merging the prompts and doing all the managing for you as well. Oh, this is an example of two computations using the same prompts, and I also put async.zip that is basically running the two computations in parallel and then getting the results, assembling both together. And I put it here to show that prompts and all these composability, they also work across asynchronous boundaries. So you can do parallel execution, you can do more advanced patterns of execution, still maintaining the same kind of behavior and the same kind of composability of those effects. Prompts also have this mechanism called reminder. It's something that I created when I was working with large contexts. So when you have completion request to the LLM, you normally have the system prompt at the beginning, and then you have some content, and then the LLM is going to be generating at the end, right? So if you have a lot of context between the system prompts and the generation, the LLM might have trouble to remember all the details of the system prompt, right? So what happens with reminders is you normally have a prompt that is well elaborated, like a big prompt like we have today, but then at the end of the context, you have also the reminder. That is basically a summarized version of the prompt, reminding the LLM of the items and specifications of the system prompt. And that helps a lot if you have like a large context in the middle. It's going to make the LLM recall that's instructions better during generation. This is another example of prompts showing the dynamic aspects of prompts. That is, you can actually perform effects there when you are assembling the prompt string. So here I'm initializing the same prompt and etc. But I created this restaurant class. And I'm going to be requesting this restaurant from the environment. So there's going to be appending restaurants in the prompt type there. And then I'm taking that restaurant, getting the name, and you're a chef at that restaurant, right? So, and if you think you can actually have like actual services, make database calls, call a vector star, so it composes well with other primitives that Go provides. And then enable it and generate the recipe with that prompt. So that's prompt, and now I'm going to show tools, and tools are really interesting because they are very convenient to define. So this is an example where I created a new case class called ingredient, where I have the name and then price, that is an integer, just as an example. And then I'm using ingredients in the list of ingredients, and I'm defining a new tool that allows the LLM to get the price of an ingredient, right? So here is just like a simple test example, just like fixing to a few, to a couple of ingredients. And the LLM, the first parameter, the tool.init, and then the type parameter there is essentially, it's the input of the tool. So in this case, I'm allowing the LLM to pass a JSON, a regular string, but I could request an actual object, and the LLM would need to provide that object with the right fields as well. And the function there can have other effects as well. So everything composes within this effect system and algebraic effects. Tools. Another problem with tools when you are developing applications with LLMs is you normally have to define the system prompt. And then if you enable a new tool in that flow, you also have to add instructions to the system prompt saying, you have this tool, you should use at these circumstances or not using these other circumstances. So you have some instructions in the system prompt. So as you include tools or you remove tools, you have to keep adding and removing things from the system prompt as well. And that doesn't compose well, because if you want to do, like, for example, experiments where I add a tool, remove a tool, or like this kind of like more dynamic patterns, you can't really like keep changing the system prompts, right? So tools in these new primitives also have their own prompts. So it's like a sub prompt. So for example, here, it's the same tool. I'm just passing a second parameter that is a prompt that is call this to generate the recipe, right? So what this is going to do, whenever the tool is enabled for a generation, that prompt of the tool is going to be appended to the system prompt. So it's automatically managing that relationship between the tool and the needs of instructions in the system prompt. This is another example that is a bit more involved, but I thought it was an interesting one to show. I mean, I added a new field review to the recipe that is a string that is, and here we have maybe that is unboxed representation of option, similar to option, basically. So here we have a maybe string, and the idea is providing a function to the LLM to generate reviews for the recipe. So it's a kind of like circular, right? So what's going to happen here? I'm going to ask the LLM to generate a recipe, pastel with a review, right? So it's going to see, okay, I have to generate a recipe. It's going to see the case class and going to see that there is a review, it's a maybe. And then it's going to see that there is a review, generate review function that's going to do what the AI needs to do, right? So it's going to pass that recipe initially to the generate review. And then I put like two steps here. So the first one is calling async.fill, that is basically repeating a computation 10 times in parallel. So here I'm going to be generating 10 possible reviews for that recipe. And then I then ask the LLM to generate the final recipe based on that review. So it's going to look at the reviews that were generated, the 10 options, and then generate the final one. And here, it's also important to highlight that once the generation of the final recipe is executed, actually the context of all the other reviews are already in the AI context. So even if you have an asynchronous boundary, what's going to happen is going to fork these 10 computations, execute it, but at the end, it's going to merge all the interactions that those computations had in the context of the AI. So once the final recipe is generated, it has all the context of the generation before with the trials of possible generations. And then we have thoughts, that is essentially this new structured thinking mechanism. It's a bit different. So if you don't know, in Scala, you can actually define fields and even methods as pure, just like regular text that is using backticks. And that's also supported by the JSON schema mechanism, and the AI providers also support this kind of format. And that's a really good way, because what happens here, the LLM is going to generate something, right? And we want to inject some thinking process that is not only just a free generation with like, as we are seeing with like the reasoning models, but something that is more constrained, that is directing the LLM to behave and analyze specific contents, right? So here, the LLM is going to fill, every time the LLM sees a field that is a text with the key, the system prompts, the default one in the library, instructs the LLM to think of that field as an opportunity for reflection and to generate and improve the generation that's going to be happening later. So it's going to first reflect on the requirements of the task, and then make up a plan of how to reply and do the completion, and then double check if any rules are broken or not. And then we can create a thought that is essentially the type, right? So I'm creating an opening thought that is analyze, and an opening thought is something that's going to be placed at the beginning of the generation, right? So it's something that's going to be preparing the LLM to generate the actual value that is, for example, what the user is asking here, that is a string, that is a plant and hunger, for example, right? And that's going to be actually out of band. So if you are using the library and you are using AI.gen and you have your codes, you don't even need to change anything. What's going to happen is from outer scope, we can enable a thought, and that's going to be injected in all generations in that scope, right? So if you have multiple generations, they all going to be generating this same thought. and it's not going to be in the response to the actual codes, like because it's going to be just a string. It's something out of band. And then, for example, here, an example generation of how LLM generates this thought before its actual response. So it's going to do like the checking the requirements and then making up like a plan of how to reply, and then like making sure that there's anything that's like breaking rules from system prompt and etc. And if you notice, it's actually a kind of like self-prompting mechanism, right? So allowing the LLM to generate its own behavior through reflection. It is similar to reasoning models as well, but in a more structured and more deterministic way, in the sense that you know what the LLM is going to be reflecting on, essentially. And then you can also have not only opening thoughts. So for example, I have here the same analyze thoughts, but you can also have closing thoughts. That is so you have the opening generation, the regular generation, then at the end you can have closing thoughts. And those closing thoughts are kind of like verification of information. So you can have like different behaviors there. Of what you want to the LM to think about, essentially. So in this case, I'm just like checking. Let me check if I followed all the instructions. So the LM reflecting if it followed all the instructions. And it's not very intuitive why place a validation like that at the end of the generation. But it's something I noticed with LLMs. They normally are much more concerns with but it's going to be still generated, like, so it's trying to produce like a chain of thoughts that allows it to spill like a lot of words that's going to be coherent, right? So it's always considering the future generation while it's generating. So if the LM sees that there's a validation at the end that it's going to have to generate, it's actually going to be planning for that, so the text as a whole is consistent, right? So it affects the actual generation, even being placed at the end of the generation. And another thing that's really important about thoughts is that they are out of band, so you can't like really do anything like in the AI.gen call, but you can actually have processing logic for thoughts. So this is something that has really good applications, for example, for business. That is, when you are starting the generation, you can ask the LLM, for example, to analyze, considering all the interactions so far, is the user satisfied? And then it's going to produce some text like reasoning about the satisfaction of the user and etc. And then I can ask for the LLM to provide a score of the user's satisfaction, right? So you can also add these annotations like description, maximum length, and etc. A few annotations to constrain the LLM as well. It shows up in the JSON schema. And then I also have verify, so a closing thought. And it's going to first like reflect if any of the completion broke any rules. So looking at like, for example, business constraints, or like you can't do anything. And there's a lot of that in prompting. But if you have something more definite like this, it's much easier to observe and direct the behavior of the LM as well. And then if you see the creation of the thoughts down there, the opening of analyze is actually passing also a function that takes the object analyze, and then I'm just like adding the user satisfaction to a histogram, right? So you can observe and have metrics for AI thoughts, right? So if you think of the applications in business context, this is something that can be really useful to have like systems that are better behaved, because LLMs can still be like misbehave a lot. So going towards more deterministic behavior, more reliable behavior. But if it doesn't behave, you have mechanisms to observe that. You can even, for example, record those thoughts as well to inspect, or even training AIs or something like that. And then the verify processing, it's actually using the broken rules detected flag to see, okay, if it broke any rules, then I'm going to fail the generation. And abort is more like an intrusive effect, because it's going to actually fail the AI.gen call. And that's the kind of behavior that you want to have, right? So if you see that LLM generated something that shouldn't be allowed in the business context rules, right? You should fail that request, not really provide that completion, for example. And we are getting close to the end. I'm sorry, maybe it's a lot, and I think I'm a bit over on time. But then I have agents and modes that are, I'm not going to go in too much details there, but agents are actually just a specialization of Q's actors for LLM generation. So this is how you can create an agent in Q. This is like a very simple run methods. You pass the prompts, you pass the tools it's going to use, the thoughts, and then the function is actually a free function. You can use multiple effects there. You can even use AI generation within the agents, like here AI.chain, or you can use asynchronous computations, run things in parallel. Agents can not only be like this unstructured, unconstrained being that's going to take text, take consistent prompts, and behave a certain way. It can be something more strict, for example, an agent that works with a specific schema in a specific constraint that you can even fine tune for, right? So you can have better behavior and better constrained behavior that way. And then the last one is modes. It's a more low level and advanced, so but I thought it was an interesting one to add as well. So modes is basically intercepting the generation call. So when we call AI.gen at the end of the example, it's going to be within a context where the mode is enabled, that is the temperature sampling mode. In that point, the library is going to pass the continuation of the generation. So the gen with the maybe A and AI, that is the parameter of the apply methods, to the mode, and the modes can do whatever with it. So we can decide to call the next generation or not, or call something else. In this example, I'm doing something I called temperature sampling. That is, instead of having a single generation from the LLM, generate multiple possible options at different seeds and different temperatures. So basically trying to find variation to reduce hallucinations. The prompt is not here because it's too large, but it's going to be in the repository as well. So it's essentially a way of like the LLM being able to generate multiple options and then look at those to see if there's like too much inconsistency to know if it's a hallucination, for example, about information it doesn't know. But you could even do something more advanced. You could do like call multiple providers and see like if they are agreeing with each other to provide and then the final result to the user. And you can enable modes for a scope. So if you have some code, some logic, doing something, you don't need to change it. You can just enable the modes for that code, for that computation, and that's going to be getting all generation there is going to be getting this new behavior. So it plugs in like everything together really well. And just to finalize, I have just a few more slides. Sorry, I'm a bit over time. There's a bonus that is the MCP server. So there's a module for MCP, and that's how you define an MCP server in Q. It's the server itself just a line, right? So it's just the run methods, but you can then pass multiple tools there, and the server is going to be serving those tools to the MCP clients. And the tool definition is the same thing. It's just like the MCP server.run is going to take a list of tools and serve those tools. It doesn't implement other features like prompts and resources, so that's something we are going to have to explore and implement later. But there's more too. So there's Go Playwright. So it's a new module. It's actually in the main repository, but I worked on it for the AI work. There is a programmatic and tool slash tool AI tool browser access. So the LM can actually access an actual browser and then manipulate and like interact with the browser there. There's a new module for integration with the neotypes library. There is a library for Neo4j in Scala. So it basically allows you to have like knowledge bases in a graph, and it's very common usage for LLM applications. And Neo4j also provides vector star, so you can do like vector search there. And the last one is Q Container, that is integration with Podman and Docker. Because I think like this paradigm where we are using MCP to build and like deliver servers to people in an unsafe way, I don't think it's really a good direction. I think AI being as powerful as we think it's going to be and already is, it's important to have isolation, etc. So the idea is to use this new module to isolate the execution of tools and provide a better and safer experience to the user. Because also containers are a good way of like not having to install things locally and having things working easy, right? So just to close up, what's next for the project? It's still, I wouldn't say we're early days because I've been using the library and etc. But um, I haven't like really set up like the artifact publishing, etc. So it's not really useful still, but it should be in the next couple of months. We are also the main focus of the project is really doing the 1.0 release, so that's going to be the priority over even the AI work. And then we have also a project I started that is tasty query integration. That is a way of reading the class path in Scala, and then the idea is to have a way of LLMs to consume Scala class path code bases in a more structured way, because Scala maintain all information in tasty files now at runtime as well. And then the Copilot itself, it's something I've been working on for a while, but hopefully eventually we are going to have, and its idea to be something that is specialized for Scala and Q, and it has like more advanced features that I'm going to be exploring later and releasing later. And that's all that I had, so thank you.
Thank you very much, Flavio. Thank you very much for an interesting presentation, and also for sharing like the interesting how you can actually programmatically start calling the LLMs from Q. Thank you very much. There's yeah, people like in the chat. There's also like love the map flat map aliasing. I think that's also good. It's a good one. It's easier for people to get started, actually, especially to functional programming or using more advanced concepts. I'm gonna ask you. I'm gonna start from the beginning. How did you come into Scala, Flavio?
It was open source.
Oh.
I was yeah, I was working with Smalltalk at the time. And then, yeah, we were migrating to Java at the company, and I wasn't really happy because Smalltalk was really good. Like I had really a good experience developing Smalltalk. And then I started searching, and someone told me about Scala, and I love the language, like especially Scala 3. The type system, like the features the language has, it's really, really accessible to build, like, especially if you're building more like advanced codes or building with more performance-minded codes, and it's really good for that.
How come you got started with Kio from the beginning, or Kaio?
I would say Kyo,
Kio.
or Kyo is fine too. No
Yeah.
worries. Kyo is fine too. Um, I would say it was a process. So I used to work on optimizing, for example, the Twitter feature that is like a component-like API. So, and then we had like also projects of batching of calls, similar to Haskell in Haskell. There's like batching requests to other services and etc. So I've been like in this domain of like computations and how to express them and how to get to good performance. So that was like the real initial motivation, like trying to find a good way of encoding computations that provide the nice behavior of like effects and being able to do things at more at a low user level that would be necessarily not have like language changes. So in that sense, like it became like a process of like getting to eventually build Kyo, right? So it was a process of like multiple ideas, multiple years, eventually getting to building Kyo.
Yeah. How long time have you been working on it? Or has it just been a process that at some point went into this project or
It was I think it's 3 years now,
oh,
probably.
yeah.
Mhm.
Yeah. And now you're soon to release 1.0, you said?
Yes, yeah.
Yeah. Impressive. Impressive. Um, will you share your slides with the audience or will you do it
Yes.
later? Yeah. We'll share
Oh,
the slides. I mean, if you put it out into any like GitHub, wherever, we'll share it with everyone afterwards, so they can find it below, you know, in the description of the video. Of course. What's anything else? I'm looking at the chat. No, people just say someone has already answered the questions that's in the chat. Well, thank you again, Flavio, and thanks for joining in. Yeah. And with that, we would like to say thank you everyone that watched and followed Func Prog Sweden today, tonight, or wherever you are. And hope to see you next time on the 10th of June. Until then, have a nice time.